This is Matthew Bauer of the Computer Science Department at Illinois Tech. This is one of a series of videos I'm doing demonstrating some course assignments in my first year courses that also touch some more advanced topics in computer science. These are normally ones I would do on a preview day open house, but I'm posting short lectures online about them. So there's a link to see all these materials. It should be in the description associated with this video. So today's topic, we're going to talk about encryption. So, the math theory for encryption is pretty advanced. It's not something that first-year college student normally works on, but there are ways to think about encryption in a more abstract way and kind of demonstrate how it works. So we're specifically going to talk about public key encryption, which is the main encryption used on web pages. When you go to a bank website, HTTPS, the S means secure, is using public key encryption. So one kind of abstract way to think about that, it's like when you go to that website, the bank puts a box out that's open, you put your stuff in the box and close it, and it locks when you close it, and send it back, and only the bank has the key to open it. So that's a very abstract idea of what public key encryption is. The open box is this public key. Anyone can put something in it. If you put something in it and you close it, it's locked and only the bank can open it. So again, that's a very basic idea of it. However, there are two ideas that are a little more insight into how public key encryption works. And the two concepts are hard problems, and we'll talk about that, and then also one-way functions. So for computers, a hard problem is one that takes a long time to solve as the problem space grows. So again, it's a little kind of an abstract idea. So it's a good example would be how if you're just counting in binary, let's say, and if you're only considering 4 bits, what's the largest number you can represent with 4 bits in binary? Okay, well, in 4 bits in binary, it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Those are the 4 bits. So you can represent up numbers between 0 and 15 with 4 bits. You add one more bit, only one more bit, and you get a 5th bit. Now you can count all the way up to 32. So adding that single bit doubles the number of options to count. Add another bit, it doubles again. Add another bit, it doubles again. It's an exponential growth. Binary, the number of bits to represent a binary number represents an exponential growth. One more bit doubles the number of numbers you can represent. So there are problems that we know an algorithm to solve, but because they're exponential growth problems, if the problem gets large enough, the number of bits gets large enough, even though we have a way to solve it, a computer takes too long to solve it in a reasonable amount of time. So for example, specifically for encryption, at one time we did 16-bit encryption. And the number theory behind it, it's trying to find factors, prime factors of a very large number. When that large number was a 16-bit number, finding the prime factors was hard at one time, but eventually computers got fast enough so they could try all the numbers less than that 16-bit number and find the prime factors just by exhaustively finding them all. So fine, when computers got fast enough to do for 16-bit numbers, they went to 32-bit numbers. Now, how many more 32-bit numbers are there compared to 16-bit numbers? There's a lot more. Remember when we just went to 17 bits, it doubled it, 18 bits, it doubled it, and so forth. So when computers caught up to 16-bit encryption, they went to 32-bit encryption. When computers got fast enough to do 32-bit trial possibilities in a reasonable amount of time, they went to 64, 128, currently 256-bit encryption is used. And the computers can't find those prime factors for 256-bit numbers fast enough. So that's a hard problem. It's a problem that grows exponentially as for example, the number of bits grows, the number of items we need to search grows exponentially. The second idea is a one-way function. So a one-way function is, you remember from your math class, many functions have an inverse and some functions don't. So certain functions you can do the inverse of. And if you think about on an xy plane, the inverse of a function is you're mirror imaging it across that y equals x. That's the inverse of a function. So other functions maybe don't have an inverse. It just doesn't exist, at least in the real plane. So we want to have some sort of function that kind of this public key encryption, putting this box out there. I'm putting this function out there. You stick your stuff in the function, and everyone knows what my function is. It's public. You stick anything you want secure through that function. That function generates an output. You can now send that output over the internet, and everyone knows the function you used. They don't know your input, but from the output, they can't go back to your input. At least easily they can't. That's a one-way function. So a kind of interesting way to think about that is like mixing paint. If I mix up a color, I know the inputs, how much red, green, blue, yellow, and the ratios, and I mix that color. I can put that color out there, and it's very difficult to unmix it and get back the individual colors and the amounts of the colors I used. So now there are problems that we can demonstrate this idea of a hard problem and a one-way function that without understanding the number theory and the prime numbers and things like that. So if you go to the web page in the link, there's one handout here on encryption, unplugged public key encryption. So this is what it looks like. So this is the public key that I put out. This is a graph. A graph is a set of vertices and edges. And I will show you how to encrypt some data in this public key. And we'll see that it's a one-way function and it's a hard problem also. So again, it's a set of vertices and edges. It's called a graph. And I'm going to basically show you how to encrypt just a single number in this graph. So people could, even people who know that this is the graph and know what you're doing, can't get your number back. So there's the graph, and the method we're going to use is we're going to take my secret number, which my secret number is 66, and I'm going to spread integers that add up to 66 across all of these vertices, all of these nodes. You can even have negative numbers in there too. I just happen to choose positive numbers. So if you add up all these numbers shown here, you will get 66. So that's the first step. Now if I would send this, everyone would say, oh, I'm just going to add up those numbers. I can get your 66 back. No, well, there's one more step before you transmit it. So the first step is spread my number over these nodes, 66. Then the next step is at a particular node, so I'm looking at this node 1 over here, I'm going to replace that 1 with the sum of its neighbors and itself. So I'm going to replace that 1 with 1 plus 3 plus 5 plus 6. So remember, it's the sum of the value that's at that node plus its direct neighbors. So 3, 5, and 6, that's 11, 14. So it should be 15. The new number here is 15. Okay, let's do another example. One down here. There's 2. So this is a 2. I'm going to add to it 3, 5, and 3. So that's going to be a 13. So I did that on all the nodes. Okay, so I'm still showing the original number, and I'm showing in parentheses is the value that was at that node plus its direct neighbors. So I'm showing both of it on this one. You can double check, make sure I did the math right. Now what we do is we erase the original numbers and we transmit the graph with the numbers in the parens. So we're going to send this. Now what I challenge you to do is from this, and even if you knew what the rule we were using, every number is the number that was there plus its neighbors, how do you undo it and get back the original numbers which add up to 66? I challenge you to try to figure it out. I mean, even in this small graph, there's a lot of possibilities, things to figure out. It's multiple equations, multiple unknowns. You could do it, but it's going to take a while. So this is an example of, so far, of a one-way function. I can get this output, and it's very difficult to go back and get the input, which was the number at each value. Now, again, you can do it, but it's also a hard problem. To try all possibilities to figure this out would take a long time. Even for a computer on this small of a graph would take a long time. So now I'm the one who, remember, I put my graph out there. That's my public key. I must have a way that I can look at your numbers and get back your number. So I need a way to still not do it the hard way, to kind of do it quickly. Well, there is a little trick. That original graph was created in a certain way. And so here I'm going to show you the solution now. That original graph was made. That's that same graph. And the nodes that are the darker nodes here are called a vertex cover. So a vertex cover means if I just look at this node, each one of the heavy nodes, and its direct neighbors, it covers all the nodes in the graph, and there's no overlap between a node, one of these heavy nodes, and its direct neighbors. So this node covers itself, this neighbor, the three neighbors. This node covers itself and its three neighbors. Every node covers itself and three neighbors. All the nodes are covered. So these special nodes, it's called a vertex cover all the vertices in the graph by itself and their direct neighbors. And finding a vertex cover is a challenging problem. If I can create it in such a way, I could start with the cover and then draw the nodes in later. I can easily create this, but it's very hard to figure it out what the vertex cover is given this graph. It's hard to find the vertex cover. However, so remember, this was the solution. So if I go just look at those nodes, those four nodes, and add up the numbers here, so that's got a 13 and a 13, that's a 26, and a 22, 26 and 22 is 48. 48 and 18 up here is 66. Those four nodes do sum to my original number that was hidden in there. So it's kind of a neat thing. It works out. And you can develop your own by you start with the heavy nodes and then you draw vertices and edges, making sure that every node is only covered by one dark node. And so you could draw a bunch of extra vertices and edges in, as many as you want, and the more you draw, the harder it is to find the vertex cover. So it's an example of a one-way function. And it's also an example of a hard problem that to try all the possibilities to find the vertex cover is very difficult. It grows exponentially. So hopefully that was an interesting experiment for you to learn a little bit about public key encryption. You can email me if you have questions about this. My email is bowerm@iit.edu.